Okay, this one is super straightforward if you've been following what we've been doing so far. Basically just saying if you have acceleration, that we can relate those to displacement and velocity using integrals, right? Because we said that velocity was dx dt and acceleration was dv dt. So therefore, velocity is the integral of acceleration dt, and position is the acceleration of velocity dt. Okay, so again, I feel like knowing more about what I do know about physics-y stuff and where this is eventually going, that we spent all this time looking at all these individual equations that when you actually kind of take a step back and look, it's like they're all the exact same stupid equation. Why did we have to learn all these individual equations when they're all the exact same thing? So I'm giving you the option, read the book and do it the book's way, do it this way and do it this other way, whatever makes the most sense to you, okay? So I'm sure there are reasons why it is presented one way. It just never made sense to me, I guess is what I'm saying. This way, because it's, I guess, more mathy, made a lot more sense to me, and it's more of a hard and fast rule. It's always an integral, and you just never have to worry about it. So basically the idea is, like we talked about, if we integrate acceleration with integration, well, just like you have here, kind of like we've already talked about. So in this example here, we have a motorboat with a certain acceleration, and it is starting at a constant velocity of 5 meters per second, and then it starts to accelerate. Okay, what is the velocity function of the motorboat? Okay, so we're going to look at a lot of problems where acceleration is constant. And this is a really big deal because basically what happens is you get used to acceleration being constant, in which case it's 1/2 at squared plus blah, 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 blah. Okay. However, and whether you know what I'm talking about or not, is fine. That 1/2 at squared thing is only true when acceleration is constant. If acceleration is not constant, like for example, you know, like when planes fly in real life, there's actually drag, you know, that like keeps them from being effective, or if you like fall into the water, there's like fluid that prevents you from whatevering moving. Okay, so in real life, acceleration is almost never truly constant. We just pretend it's constant because for the most part it's good enough. But in real life, acceleration needs to be modeled with respect to other things that are happening. So when in doubt, you can always go back to the definition that acceleration is dv dt. So acceleration dt equals dv. Okay, so whenever you're sitting there on a test going, I have no idea what I'm supposed to be doing, t naught to t final, v naught to v final, except for remember we always say that t naught starts at time equals 0. Okay, you can always go back to this definition. This is like literally the definition of acceleration in any dimension, in any unit system, in any coordinate system. You can always go back to this. So when your brain stops working, just go back to that a equals dv dt. Take integrals, make sure your, limits on your integration is good, and you're going to have it. You're going to have it exactly where it needs to be. Okay, so I have integral 0 to t. A in this case is -1/4 t dt. Velocity, dv, nothing dv is just going to be v evaluated from v to v naught. And in this case, v naught is the initial velocity of 5. So I actually can just delete this and call this 5. But what I'm really trying to emphasize to you is it's that definition of velocity that's really the most important thing. All right, so what is that? It's like -1 over science. T squared? No, that's the opposite direction of the way I wanted to go, right? Because that's 8, right? Because the 2 times 8 makes 1/4. Yeah, okay. Evaluated from t to 0, and that's v minus 5. It's -1/8 t squared plus 5, and that equals velocity. Did I get that right? Yeah, okay. So what is the velocity? So this is the function of velocity. So at any given time, If you want to write it like a function, you can. Velocity at time t is equal to that. So you give me a time, I can tell you how fast we're going. Okay, at what point does the velocity reach 0? Well, because I'm super good at word problems, when does v equal 0? Well, when does equals 0? I don't know. When does this equal 0? Boop, boop. T squared equals 40, so t equals plus or minus the square root of 40. Well, obviously we're not talking about negative time. I lost my calculator app. Hold on. Maybe I can find it. Okay, I found it. So it's this dude, plus or minus the square root of 40. And obviously I don't care about the negative part. Come here, chicken. So 63.2 or 6.32. So it takes me 6.32 seconds to get down to a velocity of 0. What is the position function of the motorboat? Okay, so again, going back to base principles, I know that velocity is dx dt. Oops, not dx dx. dx dt. So I know that negative 1/2 or negative 1/8 t squared plus 5 dt equals dx. Okay, and I can integrate, and from an initial time of 0 to some random t, from an initial position, we'll just start at 0. Again, this is a big assumption. We're just assuming we start at 0. We just hope the problem would tell us if it wanted us to start someplace else. So we'll go negative 1 over 20, I can't spell, 1 over 24t cubed plus 5t, going from t to 0, x minus 0. I mean, I guess I could have written, and then x evaluated from x to 0. So negative 1 over 24 t to the cubed plus 5t equals x as a function of t. So that's our position function. Let's see if that's right. I just feel like I need to check. Yeah. Awesome. And see, it does all this stuff with like this C2 thing. You don't have to do this C2 thing if you set your limits on your integration correctly. So they're having you do all this extra stuff because they're assuming you can't calculus. But if you can just calculus, then you don't have to learn all this extra stuff, which was the whole point of taking calculus before you took this class to begin with. Okay. Last question. Oh, second to last question. What is the displacement from the time it begins to accelerate until when it's 0? Oh, so we just plug in that t. Well, that's not very exciting. Negative 1 over 24 times that cubed plus 5 times that. Negative 333, so I move 333. Am I in feet or meters or what am I in? I must be in meters. Negative 333. Whoa, I really can't math. 333 meters. This is doing something weird. Did I do something wrong? Maybe I did. Let's see what happens. Did I? Oh, I put them all in as multiplication instead of as in a plus sign. That's why it doesn't make any sense. It's like, that seems really big. Okay, 21.1. There we go. So x equals negative 21.1 meters. Yay. All right, and then finally, let's graph the velocity and position functions. I'm going to go ahead and do that on Desmos just because I feel like that's going to give me a prettier graph that I can actually make more sense with. Desmos, beautiful free math, open graphing calculator, and science myself along. So I've got x, I'm not going to call it x, I'm going to call it position of t equals, I already forgot. Oh no, this is acceleration. Acceleration at t is negative 1/4 t. And then velocity of t was negative 1/8 t squared plus 5, and the position of t was negative 1/24 t cubed, cubed plus 5t. Okay. And I'm not using x because it does weird things when I put in an x. Okay. Thank you. Ponk, 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 ponk. Oh, it doesn't like this one. I'll just call it position of t. Okay. So if I'm just looking at the position is, feels like it should be going down. Velocity is going this way. Velocity is decreasing because it starts at 5 and it goes down. Acceleration. Position. Why is it acting like my position goes up? I don't like this. Negative 24. Did I put that in right? Negative 24 times t cubed plus 5t. And I did put that in right. So, position versus time. Oh, because it's still, okay. It's still going forward. I guess that makes sense. Why did I get a negative sign then? I didn't get a negative sign. I just wrote a negative and y'all didn't even say nothing. You're like, we did say something. You just ignored me. Okay. It didn't go backwards because it was not decelerating. Okay. Whew. See, this is why you need to pay attention. This is why I need to graph things. Okay. So, let's see if this makes sense. Because he's going, and then he starts slowing down until he stops at, what did we decide he stops at? 6.32? So let's see what happens. Let me stop this at 6.32 and 0. Okay, so that's where he stops. So he goes here and see how the position normally would start turning around and going backwards, and that's because the acceleration would turn around, because if he keeps decelerating, eventually he turns around and goes backwards. So the velocity, he's slowing down until he gets to 0. His acceleration just keeps getting more and more and more decelerating. Okay, does this kind of make sense? I feel like I could have done better, but you know, what you gonna do? Okay, so we have this acceleration. He gets more and more and more accelerating-y. So that means his velocity reduces, but reduces by considerably more and more and more. So it's not just a straight line, it's a curve. And the position kind of starts generally going straight, because the velocity, you can't really tell. It's pretty straight for a while. Kind of straight, but then reduces and then really like tapers off right there at 6. So technically if I go here, when I go past that point here, if I go t equals 6 or square root of 40, or let's call that x. There we go. This is like that point. I don't know if I'm allowed to. Okay, I'm not going to worry about changing that color right now. But there we go. Okay. So that's like the line where we stop moving, right? Because that's where velocity. Kind of see what's going on? This blue line is velocity. So that's where velocity goes to 0. So that's where we stop. You can see that with the position, because that's what the position stops going forward and starts turning around, which is an indicator that something has happened. Interesting. And then the acceleration just continues to increase in magnitude, but decrease in absoluteness. That's not the right way to say it. It keeps getting super duper more decelerating-y. So it decelerates more and more and more and more as we go. So Maybe graphing it helps you, maybe it doesn't, but I do like putting these in Desmos because then I can do stuff like this and I can be like, okay, I'm just going to look at acceleration. Now I'm just going to look at these two together. Now I'm just going to look at this one. Now I'm just going to look at these two together. Looking at these two together is never helpful because one of them is a second derivative of the other and that's just too much. But maybe just putting it together like this would be helpful. So that should give you enough to start playing with these problems a little bit.